Welcome back. It is the third video for the 1998 AP Calculus AB, Section 1, Part A. The first video we did 1 through 10. The second video we did 11 through 20. This third video is not going to do 21 through 30. It's going to do 21 through 28. That is not a mistake. The reason we're not going to 30 is because way back when in 1998, Section 1, Part A only had 28 multiple choice questions. The more modern exams go up to 30. 1998 is not considered modern by any means. All right? This test was made before you were born, probably. So, let's get going. They start us out with a doozy, okay? 21 is if dy dt equals ky, and k is a non-zero constant, then y could be. All right? They give me the derivative. I need the original equation. Okay, I need to integrate. But I have, okay, the derivative of the dy with respect to dt equals some constant y. I need to use separable differentiable equations. Okay? So, first of all, let me start out by saying something I say every time. If I have a derivative, in this case they're calling it dy dt, and I want the original equation, which they're asking for y, this way is derivative, this way is integration. That's how we know we need to integrate. All right? That's the first step. So what I'm going to do is set this up as follows. I have dy dt equals ky. Now, k is a constant. It's 5, 7, -2, as long as it's not 0, okay? Because if it was 0, on the right side, 0 times y would just be 0. It'd be good to go. I'm going to get my y's and my dy's alone on one side. So I'm going to multiply this by 1 over y, and these go bye-bye together. I multiply this side by 1 over y. I need to get my dt on the other side with the constant. So I'm going to multiply this by dt, multiply this side by dt. What's left is 1 over y dy equals some constant dt. Okay? I need to integrate both of these. That's how I'm going to pull my y out. Okay? My y equals out. So when I integrate this, and I integrate this side, okay, my rule, what do I take the derivative of? That's 1 over y. How about the ln of y? But guess what? There are no bounds. Plus some constant c. Okay? Now the integration of k. K is a constant. Okay? Let's say k was 5. Okay? What do I take the derivative of? That would give me 5? Well, 5t. Okay? I don't know if it's 5. Maybe it's 8, so it should be 8t. Maybe it's -8, so it should be -8t. I don't know what that constant is. I just know when I integrate it, I just slap the variable onto it. So on the right side, I'm going to have k with my variable t. Remember, our variable is t. Again, there are no bounds. Plus c. All right? That 8 is not a bound. I was just making an example of integrating any constants. Right? So I have this. And the first thing I want to do is I want to get rid of the constant on the left. Remember, these could be different constants. They don't necessarily, they're not the same constant. They could be, but it's not guaranteed that they are. So if I subtract one constant away from another constant, I still end up with a constant. So I got k, t, plus some constant. If you want to call that C3 or just C at this point, okay? It's just going to be some constant. Let's continue up here. So now I have the ln of y equals kt plus c. I need to rip that y away from the natural log, and I'm going to do that by just putting a base e to both sides. Okay, bye-bye. There's my y equals. Now, who here remembers our rules for exponents? Okay, how do I add exponents? I add exponents by multiplying similar bases together. Okay, if you forgot that rule, you best remember it. If you're looking at this screen like you're all confused, remember, x squared times x to the fourth is x to the sixth. How come? Because this is 2 plus 4. Okay, I add exponents. So how did I add exponents? I multiplied them together first with similar bases. Okay, I multiplied the base and I add the exponents. All right, here we go. E is a constant, okay? And C is a constant. If I have a constant raised to a constant, that's still a constant. Okay? That is still a constant. All right? Now, I don't know. Let's say it was 5 or 3. Why don't we put that in front of the E? We would. We absolutely would. And there, my friends, that I feel comfortable with that. Y equals that bad boy right there. So which one of these could represent this right here? Notice you don't see C, E, K to the T. I don't see a C anywhere in these answers. Could be. Which one of these answers has e to the kt times some constant? Choice 2 has e to the kt times some constant. That was a doozy to start off with. That was a good problem to figure out. And now let's go on to 22 and relax for a bit. The function f is given by f of x equals x to the fourth plus x squared minus 2. On which of the following intervals is f increasing? All right. In order for f to increase, that means the first derivative needs to be positive. All right. So let's find the first derivative. That's 4x cubed plus 2x. Okay, and then the derivative of a constant is 0. Let's figure out where it's equal to 0. Those are our possible critical points. And then we'll figure out in between those zeros if the first derivative is positive or negative. So factoring never goes away. All right? So I'm going to factor out a 2x, and that leaves me with 2x squared plus 1 equals 0. Now I'm going to solve for each one of these. This set of parentheses is unfactorable, okay? 2x equals 0. That only happens when x is 0. And guess what? This will never equal 0, okay? How come? It doesn't matter what value I put in here. When I square it, it's positive. When I have a positive value and I add it to 1, it will never go down to 0. If you wanted to try to subtract 1 from both sides, okay, 2x squared equals negative 1. Divide by 2, x squared equals negative 1/2. This is where the issue happens. When I take the square root, I can't take the square root of a negative number. So guess what? The only place where my first derivative is equal to 0 is when x is 0. So let's just create a little chart right here. So when my x is 0, that's when my first derivative is 0. And let's pick a number on both sides to put into our first derivative. Positive 1. Okay? If I put a positive 1 here, that's 4 times 1, plus 2 times 1. Okay, that's a positive value. If I put a negative 1 in, okay, I put a -1 in here, I get -2. If I put a -1 here, I get a -4. Okay, that's going to give me a -6. That's negative. Keep in mind, we want this. From 0 all the way over will always be positive. Okay? From 0 to infinity and beyond. Oh, man. If you guys have been watching these videos, you know I love me some graphs. 23. The graph of f is shown in the figure above. Which of the following could be the graph of the derivative? Okay. The first thing we need to do is establish this is f. One of these is going to be the derivative of f, okay? That represents the slope, okay? The slope of f. And this is what I like to do. First of all, okay? I don't have the time here. I don't have the space here. I like to do this right underneath it. So can I do this? Okay, look at that. Okay, I see what I did here. Let's move these all down a little bit and give myself some room on the graph. Get rid of these. Bang, 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 bang. See ya. It's like a flock of bees. Now, I'm going to create just a little graph underneath it. Same exact. Here's B. Here's the origin. Here's A. This, what I'm going to do is I'm going to sketch the graph of the derivative right below it. Now, the first thing that sticks out to me, where is the derivative 0? Derivative is the same thing as slope. So the slope is 0 right about here. So right about here, my derivative, which is the y value of this graph, should be 0. So I have a point here. It's actual coordinate. It's a 0 of that graph, or an x-intercept. It looks like, I don't know, I mean, this is kind of 0, horizontal line, and this is. So at point A and point B should be another 0, or x-intercept, when I'm graphing the derivative. So let's look in between those points. At the graph up here, in between my horizontal lines, this part of the slope is positive, which means the slope or derivative should be positive between these 2 points. And the slope here is negative. Okay, so my derivative is negative. Okay, keep in mind, for the graph below, the y value is the derivative. Aren't the y's positive above the x-axis and negative below? So if I'm looking at this right here, in between these 2 0 points, I should have negative y values down here. And when I look at this, between A and, I don't know, whatever other horizontal line is, I don't know what number that is, 1, 2, whatever. That's all positive. So it makes sense that for my derivative graph, it should all be positive y's, or above the x-axis. So my graph should look an awful lot like that sketch I have below the one they gave me. And that, my friends, is right here, choice A. 24. The maximum acceleration attained on the interval between 0 and 3 for time, or for t, whatever t is, by the particle whose velocity is given by v of t equals t cubed minus 3t squared plus 12t plus 4 is. All right, well, first of all, I need acceleration. And there's position, velocity, and acceleration. That's one derivative away. Okay, so I need to take the derivative of velocity. That's acceleration. The derivative of t cubed is 3t squared, minus the derivative of 3t squared is 6t. The derivative of 12t is just 12, and the derivative of 4 goes bye-bye, okay? So I got to find the max value on here between 0 and 3. All right, well, I mean, let's factor out a 3 first. I'm going to take 3, end up with t squared minus 2t plus 4, okay? So what I'm going to do, all right now, is I am going to figure out my t value is and figure out the corresponding a of t is. I'm going to literally calculate from 0, 1, 2, 3, okay, the actual values for acceleration. I just want the biggest value. It's that simple. Now, keep in mind, kids, keep in mind, all right, that this is a parabola. This and this are parabola. So it's opening up, okay? It's opening up, meaning if I put a 0 in for t, all right, where are we? I put a 0 in here and a 0 in here. I get 4, all right? Okay, because this goes by this. I get just 4. 4 times 3 is 12. So I'm going to do this for all of my t values. 1. 1 squared is 1. 2 times 1 is 1, so 1 minus 2 is negative 1, plus 4 is 3, and don't forget I got to multiply it times 3. So that is 9. All right? Do it for, let's go a different color. Orange. 2. 2 squared is 4, minus 2 times 2, well, I mean, that's also 4. 4 minus 4 is 0, plus 4. Okay, and then 4 times 3 again. It's 12. And now let's go gray. Okay, I'm going to put a 3 in. 3 squared is 9. Minus 2 times 3 is 6. Plus 4. Okay, that's 3. That's 7 times 3. That's 21. Okay, the maximum acceleration in this interval. Yeah, if I went to 4, it'd probably get higher. But they only want from 0 to 3. That was almost like an Algebra 1 problem once you got to the acceleration. That was a good one. Number 25. We're moving now. What is the area of the region between the graphs of y equals x squared and y equals negative x from 0 to 2? So I'm going to sketch this because, you know, I like drawing. All right, here we go. Here we go. Here's 0, 1, 2. 1, 2, 3, 4, and 1, 2, negatives. Okay, the graph of y equals negative x is a straight line that goes through down 1 over 1, down 1 over 1. Boom, continues. This is y equals negative x. The graph of y equals x squared, 1, 1, 2, 4. It's part of a parabola. Okay? We're kind of continuing. So y equals x squared. They want, oh, I like when I get to use my lines, between 0 and 2, this area between the curves. Now, I need to find out this area right here, which, by the way, is going to be easy. That's a shape. I don't have to integrate that. That is a perfect shape. That's a perfect triangle. I'm going to actually use the area of a triangle. This one, however, that, my friends, is not a perfect triangle. That we're going to have to actually integrate. All right? So let's find out the area of my triangle first. This has a height of 2 and a width of 2. So 1/2 base times height, right? Half of 4 is 2. So this area right here is 2. I'm going to take that area and add it to my area here that I have to integrate. From 0 to 2, because that's what they tell us, my equation, x squared dx. So whatever this is, I just add to 2. Let's go. 2 plus, okay, that's going to be x cubed over 3 from 2 to 0. All right, not too bad. 2 plus That is 2 cubed over 3 minus 0 cubed over 3. This goes bye-bye. So I end up with 2 plus 8 thirds. Oh, it would have been cool if they had 2 and 8 thirds, but they don't. So I'm going to make this 2 into a fraction so I can combine it. 2 is the same thing as 6 over 3. Okay? That gives me 14 over 3, and that is a solid answer. That is a solid answer. Boom! That was a good question. I like that question. That was a good question. Hey, 26. The function f is continuous on the closed interval from 0 to 2 and has the values that are given in the table above. The equation f of x equals 1/2 must have at least 2 solutions in the interval from 0 to 2 if k is what? They're saying what value would be here. All right, let's visualize this, okay? Let's visualize this. Draw a little graph here. Draw a little graph here. Okay, when x is 0, y is 1. Okay, so let's put a point right there. We don't know about when x is 1. We're trying to find that k. But when x is 2, y is also 2. All right, now okay, it's all positive. So put a point at 2, 2. So we just graphed this point, 0, 1, and this point, 2, 2. Okay, we've got to figure out what this coordinate with the y value of that coordinate when x is 1 would be. But here's the kick. It's got to have 2 solutions to x equaling 1/2. So here's where x equals 1/2. Okay? So along this line, okay, I need to have 2 solutions. Again, this is almost like an Algebra 1 problem where in order to have a solution, you've got to have your 2 graphs intersect. Meaning, if I put a point, all right, if I put a point at 1, if k was 1, okay, let's put a point 1, 1. This graph wouldn't touch it at all. It would have 0 solutions, possibly. Okay? So what I want to do is find a value that goes below 1/2. Okay? I want a value that goes below 1/2. The only thing that I see on this list that's below 1/2 is 0. So if this was 0, the point would be right here, which means I have to cross 1/2 at least once to hit here, and then I need to cross 1/2 again to climb all the way up here. Maybe there's more than 2. Maybe it does something like this. You know, I don't know. But at least 2 means it has to start above, come below, and go back and rise above my value of 1/2. The answer is k should be 0 to guarantee that. 27. Okay, we're going to do a little bit of work for 27, but that's okay. That's what we're here for. What is the average value of y equals x squared times the square root of x cubed plus 1 on the interval from 0 to 2? First of all, they are not asking me for the average rate of change, which would just be slope. They're asking me for the average value. Anytime I take the average value of an equation or function, I should say, I take my function, I integrate it from my bounds, but then I got to multiply it times 1 over the difference of those bounds. Now, I know some people, instead of multiplying by a fraction, they just like to divide by the b minus a. And that's fine, you can do that. But the way I set it up is I leave it like that, and how come? I leave it like that because you never know when you're going to get fractions as answers. And for 27, you'll see we got a lot of fractions as answers. So let's go through and put in what we have here. All right, so let's erase this. Our bounds, oh man, that was a big one. Our bounds, okay, they go from here's A and B, so they go from 2 to 0, which also means 2 and 0 are going to go there. All right, and now we're going to put our equation of x squared times the square root of x cubed plus 1 dx, okay? So we're going to integrate this from 0 to 2, and then I'm going to multiply it by, this ends up being 1/2, okay? All right, well, that might be tough to integrate, but for the trained eye, and you guys got to train your eyes to see this, I see the derivative of one function here, at least most of it, the important part of it. If I take the derivative of x cubed, I'm going to end up with x squared, like 3x squared. The constant isn't the important part. It's the x squared is the important part. Because of this, I'm going to use u sub. All right? I'm going to say, well, my u is going to be x cubed plus 1. So the derivative of that is 3x squared dx. What I want is I want to substitute something in for x squared dx, which means I want to keep the x squared dx on the right side. Let's get rid of that 3. So we'll multiply both sides by 1/3. So 1/3 du is going to substitute in for x squared dx. So this is going to go bye-bye, and so is this. All right? So let's start to make this happen. I have my 1/2 here. All right? I'm going to integrate this. And in for x squared dx is going to be 1/3 du. I'm going to put my du here, and my 1/3 is a constant, so I'm just going to put that on the outside. Multiply the outside. It's good. In for this right here is u. Okay, so I'm going to put u here. And I'm going to change that square root to an exponent of 1/2. Remember, the inside has an exponent of 1. The outside, if it's not written, is 2. Top down, bottom out. Okay, bottom was the one that's out, so that's the denominator. The top is the one that slid down, that's the numerator. Okay, so that exponent should be 1/2. That should be known. You should know that. Square root is an exponent of 1/2. My bounds. Resist the urge to put 0 and 2 here. If I changed everything into u form, okay, these are currently at x equals 2, at x equals 0. Notice there's all u's now. So I want u for upper bounds, and I want a u value for my lower bounds. And I use this right here. For my upper bound, x equals 2. So I'm just going to plug a 2 in for this x. 2 cubed is 8, plus 1 is 9. So that's my new upper bound. For my lower bound, my x value is 0, which means I'm going to throw a 0 into this x. 0 cubed is 0, plus 1 is 1. Now I am good to go. I can integrate this, and I never have to bring any x's back in. That is really, really good. That is legit. I like it. All right. The integration to this, I add 1 to my exponent. So plus 2 over 2. That's 3/2. Then I divide by the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I'm going to go ahead and multiply. But ooh, that's man, that's a small eraser. Holy cow. Okay, and I want that from 9 to 0. And oh, by the way, let us not forget, we still got to multiply it by this. 1 over 2 times 1 over 3 is 1 over 6. I'm going to multiply that result by 1 over 6. All right, so 2/3 times 9 to the 3/2 minus 2/3 times 0. Yep, that should be a 1. Woo! I almost went with this bound. It's this one. Okay. 1 to the 3/2. Okay. Take this and multiply it times 1/6. All right. The square root of 9 is 3. 3 cubed is 27. 27 times 2 is 54/3 minus square root of 1 is 1. 1 cubed is 1. 1 times 2/3 is 2/3 times 1/6. This bad boy comes for the ride. So I have 1/6 times 52/3. Okay? When everything is all said and done, I end up with, no, does 3 go into 52 evenly? 1, 22. It does not. Does 6? No. But guess what? 18. Oh, I could have reduced this. We're not going to do that. That's poopiness. Okay, so I'm going to end up with 52/18, but I know 2 goes into both of those. I can reduce that to 26/9. Wow. That was a lot of work for multiple choice. Now, I wonder why there's only 28 questions instead of 30. I'm teasing, but I'm not really. 26/9. That's the type of problem you're probably going to rewind and watch certain parts of it again. I mean, look at that. It's a lot of work for a multiple choice problem without a calculator, you know? But you're here and you want this. You want this bad, so you got this and you can do it. 28. I just want to say, video 1 was 10 problems. Video 2 was 10 problems. And this video is only 8 problems, yet this video is the longest one. These are some complicated problems. They got tougher as we went to the back. This is easier. I know you see that tangent, and you're going to immediately think that it's trigonometry, and it's not. But as long as you know your trig, you're good to go, including, I think we might need a special triangle. We'll see. So it says, if f of x is tan of 2x, then find f prime of x at pi/6. If you don't know, pi is 180 degrees. Divide that by 6. So really, that's 30 degrees. Okay, let's establish that. That's like saying the derivative at 30 degrees. All right? Your trig rules for derivatives. The derivative of x. The derivative of tangent is secant squared. This stays the same. Times the derivative of the inside, which is just 2. I will put that out front. That is a rule. We use the chain rule. Don't mess that up. Don't say it's a secant squared of 2. Okay? So here we go. Here we go. I want this when x is 30 degrees. Okay? At an x value of pi/6, which is 30 degrees. I always like to work in degrees, and then if I have to convert it back to radians, I will, but I won't in this instance. So let's put a 30 in for our x, okay? 2 times secant squared of 2 times 30. Oh, that's nice. This is just going to end up being really 60 degrees. 2 times 30 is 60. All right? You're going to need your special triangle. All right? You're going to need your special triangle. I can hear someone right now saying, oh my God, but it's only for sine, cosine, and tangent. Don't worry. We're good. Here's 60. Here's 30. There's 90. You need to know the sides of a 30, 60, 90 triangle. 1 square root of 3 and 2. Okay? So here's the problem. Well, it's not a problem. For you it might be. For me it's not. I'm going to tell you so that in the future it's not a problem for you either. We know cosine, okay, that's adjacent over hypotenuse. We know sine, that's opposite over hypotenuse. We even know tangent, that's adjacent. excuse me, opposite over adjacent. All right? Secant is the inverse of this. So secant is hypotenuse over adjacent. Okay? So we're at 60 degrees. How do I know that? 60 degrees. Opposite of 60 is radical 3. Adjacent is 1, and hypotenuse is 2. So the secant of 60 degrees, hypotenuse over adjacent, that's 2. All right? So the secant of 60 degrees is 2. Rule of thumb in my classroom, anytime you see something like this, automatically rewrite it like this, okay? Because you've got to do the trigonometry first. And don't forget we're multiplying it times 2. We just said the secant of 60 is 2. And now it becomes cake. 2 times 2 squared. That's 2 times 4, which is 8. All right? So if you know your rules for trigonometry and your special triangle, this really becomes easy. But they test you on a lot for this problem. You need to know that secant is the inverse of, or the flip of cosine. You need to know your special triangle, okay, 30, 60, 90 triangle. You need to know your derivative rules for tangent. You need to know the chain rule. And you need to be able to convert from radian to degrees. That's a lot of content to test you on for one problem. But guess what? You know it. It's cake work. We're done. Ring that bell, give it a like, give me a follow, because guess what? We are got a video 4 coming up. I would tell you what numbers they are, but I don't know because these old tests have these weird numbers. All right? I'll see you later. Bye-bye.